Alright, hello YouTube. I wanted to make a video to share with you a beautiful answer that I read the other day on a website called Quora. I'm going to link you to that website in the description box below. So the original question concerns this mathematical identity called the Basel problem, which I'm going to discuss in a bit more detail. I wanted to share with you this answer that this person gave. So I'm going to start with a bit of a story. So it's lunchtime and you and your friend here can't decide where you want to eat. So you're going to propose the following game. You're going to close your eyes, you're going to select a street at random out of this window over here, and your friend does the same thing. Okay, so whoever chose the closer of the 2 points, you're going to visit that street and you're going to look for the nearest restaurant. Okay, so here's a simple question. What is the probability that you end up going to the street that you select? Okay, so your randomly chosen street can either be closer or further than hers. And if you select from the same probability distribution, then the symmetry of the problem demands the two events are equally likely. Okay, so that's a 1/2 chance or a 50-50 chance that you end up going to the street that you pick. Now, to be clear, you and your friend each select the zenith angle uniformly. Okay, so that means that any angle between 0 degrees, that's vertical, and 90 degrees, that's horizontal, is assigned an equal probability density. The azimuth angle is irrelevant here because we're interested in the distance of your chosen point from the base of the apartment. Now, it does sound like a very trivial observation that you have a 50% chance of picking the closer of two streets, but there is a beautiful connection here between this quoted probability and what we call the Basel problem. Okay, so that's this identity that you see here, that pi squared on 6 is equal to the sum from 1 to infinity of these reciprocal squares. Now, it's a recurring theme in mathematics that we find surprising connections between facts and phenomena that seem to be unrelated at the superficial level. And in this video, I'm going to discuss the Basel problem, the Cauchy distribution, and also the distribution of the ratio of two random variables in general. I'm going to explain why the 50% probability that I just quoted tells us that this infinite sum here equals pi squared on 6. You know, how on earth are these facts even connected? So, first of all, a bit about the Basel problem. This identity here has got a special place in the hearts and minds of all mathematicians, but especially the analytic number theorists out there. And there are many ways to prove this result. I'm going to start by talking about the standard way of proving this result. Okay, so we're going to start with this function here, the absolute value of x defined from negative to positive pi. Okay, so here's pi. This is the absolute value function from negative to positive pi. Okay. And the way we can express f of x as an infinite series where the coefficients are defined thus. Okay, so this is the Fourier expansion. So the C0 coefficient is just pi on 2, that's the average value of the function in question, and all other coefficients in the Fourier expansion representation is just from this product integral. And it's a very well-known result that the Fourier series of a continuous function, compactly supported like this, will converge pointwise to the function in question. And to calculate the Fourier coefficients, we can just apply integration by parts. And if we're careful with the absolute value symbol, we realize that the negative part from negative pi to 0 is actually just the complex conjugate of the other half. So the imaginary parts actually cancel. The Fourier coefficient ends up being 0 for even values of k, and it becomes the negative reciprocal squared for odd values of k. Okay, so if you substitute the original, if you substitute the coefficients into the original Fourier expansion, we end up with a series that will match the original function. And if you substitute x equals pi, the left-hand side becomes pi. If you substitute x equals pi, the left-hand side becomes pi, whereas the right-hand side is pi on 2 plus 2 on pi times this infinite sum of odd reciprocal squares. And we conclude that the series of odd terms sums to pi squared on 8. Now, if you look back at the original sum, notice that 1/4 of it is a series involving only even terms. Okay? So the series with only odd terms is equal to the remaining 3/4 of the original sum. So there you have it. 4/3 of pi squared on 8, or pi squared on 6, is the value of the original sum. Okay, so that's the standard way that we prove this very well-known mathematical result. Now, so that's one way to solve the Basel problem, probably the best known way, but in this video I want to share with you a different and very surprising connection with the opening story. So once again, I want you to imagine that you're looking out the window, so here's you, and you and your friend each choose an angle theta from the vertical, so this angle here, which is distributed uniformly on the open interval from 0 to pi on 2. Okay, so each angle gets equal probability density, that's 2 on pi, normalizing the total probability to 1. And this choice stipulates, whatever realization you get, it stipulates some physical distance from the base of your apartment, which is 1 unit high. Now, the chance that x is smaller than a given number, little x, is a probability that tan theta is less than x, or that theta is less than arctan x. So the cumulative distribution of this random variable x is just 2 on pi arctan x. So the derivative is a probability density function for x. By the same argument, your friend picks the same density function for y, and if the two of you select independently, the joint density function is simply going to be the product of the two. Now, how is this connected to the Basel problem? Well, I started this video by asserting that x is less than y with probability 1/2. But that's another way of saying that the ratio r of random variables x and y is less than 1 with probability 1/2. So what if we knew the distribution for r? Then we could integrate its probability density function between 0 and 1, and it must equal 1/2. So here's the punchline. The integral is actually going to look a lot like the series in that Basel problem. But we have to do a bit of work to show this, okay? So consider the general case. So suppose you've got two random variables, x and y, with a joint density function rho. Okay, what is the probability density of a new random variable r defined as the ratio x on y? Okay. Well, the probability of an event is defined as the integral of those corresponding points in the sample space integrated against the probability measure, which is rho dx dy. So this Dirac delta function here selects out the relevant points in the region of interest, namely the points where x and y is equal to some fixed number r. So consider a simple change of variables to new variables z and t, where y equals t, and z is conveniently chosen to be the contents of this Dirac delta function. Okay, so this removes the integration over z, setting z equals to 0. And when we apply this change of variables, okay, we must never forget the Jacobian. In this case, the Jacobian evaluates to t. So we need to sweep out all x and y from negative to positive infinity. And if you think about it carefully, sweeping out all z and all t from negative to positive infinity will actually represent each pair x and y exactly once. So, in summary, we have a formula for the probability density of the quotient of two random variables. Okay, and here it is. So let's just plug in the joint density function to get the quotient of those two values in our problem. Okay, so back to the story. We're just going to plug in that joint density function, and this integral looks intimidating, but it's really not. Okay, so we can actually split it using partial fractions, and we can even avoid imaginary numbers. So if you use partial fractions, you do end up with this factor of 1 on 1 minus r squared out the front, and we can then actually just evaluate the antiderivative at t equals 0, which gives 0, whereas if t tends to infinity, gives 1 on r squared inside the logarithm, if you apply the L'Hopital rule. So I began this video by saying that you have a 1/2 chance of picking the closer of two streets, and integrating this probability density of r, the ratio of x to y, from 0 to 1 must therefore equal 1/2. The last trick that we do here is we express this factor 1 on 1 minus r squared as an infinite geometric series. So if we interchange the limits, we integrate each term by parts, and the second piece in each integral evaluates the reciprocal of an odd square. The boundary term vanishes once again by the L'Hopital rule. So if you remember back to the beginning of this video, we know that the full series, comprising the odd and even terms in the Basel series, is actually 4/3 of this sum. So there you have it, the Basel problem as it relates to the problem at the beginning of this video. Thank you.